So, thanks everyone for having me here. Yeah, really appreciate the opportunity to speak to you all. And we got a lot of stuff to cover, so let's get into it really quickly here. So if you didn't hear, my name is John Simpson. You can find me on Twitter at Thraki, and let's get going. So who am I? Staff researcher on Trend Micro's N-Day vulnerability research team in Toronto, Canada. Previously, I was a Big Four consultant. I did SOC engineering, pen testing, vulnerability assessments, and secure code auditing. And I've been a lifelong Linux nerd. I started back on the 2.0 kernel when I was 12 years old. You basically had to recompile your whole kernel just to get your network card working, and that's kind of where I really kind of got my start. So a little bit of background information on what we're going to be talking about. On February 2020's Patch Tuesday, Microsoft released a patch for CVE 2020-0729, and the title was Link Remote Code Execution Vulnerability. So based on prior research our team performed in 2018, I had a general idea of what was going on with the vulnerability. It involved the exact same function as the previous vulnerability, which was that CVE from 2018. But I wanted to expand on our previous research by documenting all the structures leading to the vulnerable part of the file. Due to time constraints, we didn't fully explore a lot of those parent structures in 2018, and the end result of my work was basically a very detailed research report, most of which you can read on the very long ZDI blog post from March 26th, so you can check that all out on the ZDI blog. So the ZDI blog post contains all the extensive detail on the structure of saved search link files that was basically the result of my research. I could just read it to you, but that's not really terribly interesting since the information is already there and it's already public. This talk instead is going to focus on how I approach this specific problem, and we're going to look at the tools and some of the techniques I use to document an unknown or poorly documented file format. Okay, so first let's talk really quickly about the vulnerability itself. We're not going to get into a lot of detail on it, but just so you have a little bit of background of what we had as a starting point. So nested deep inside link files that have saved search data, there's structures called property variants, or prop variants for short. Prop variants are basically just property fields that have a type followed by data according to the type. So it's basically sort of like a type length value type field, except it doesn't always have the length. It depends on the field type itself. So one particular type, VT variant, means that another prop variant immediately follows it. And this particular type is usually used in conjunction with a flag called VT vector, which basically just means that it's going to be an array of that particular property variant. And in this case, it means basically an array of mixed types. However, when you encounter a VT variant that doesn't have that flag set, so there's only going to be one additional prop variant as part of the VT variant, it allocates a 24-byte buffer and doesn't initialize it. So what that means is that the buffer may still contain data from previous use of that memory location. Now, if the nested property is VTCF, which is a property that's supposed to contain clipboard data, it attempts to write the next 4 bytes of data from the file to an address pointed to by an 8-byte value in the uninitialized buffer. So basically what that means is that with enough heap layout manipulation, this could potentially allow writing of 4 bytes to any writable memory location, which is obviously pretty bad. So now what? Well, documenting a binary format generally requires three types of tools, I should say. Number one is a tool for static analysis of the file. You can use a simple hex editor. In general, I would lean more towards something like 010 editor or KaiTai struct, which allows you to build a parsing template as you go and actually be able to parse your file and see what happens when you apply generic structures to the whole file. You'll also obviously need a tool for static analysis of the code. This can be IDA, Ghidra, Radar, whatever works for you, doesn't really matter. And then you also will need something for dynamic analysis of the code. Obviously, any debugger will do. However, WinDbg Preview is pretty amazing, and it's going to make your work on Windows targets 1,000 times easier, and I will explain that in a fair amount of detail. So getting started on a problem like this can be really difficult. Why you're documenting a particular file format does make a big difference in how you start, and it does tend to be easier to pick a starting point when you're analyzing a known vulnerability. If you're building out structures for another purpose, for example, you're wanting to build a bunch of test cases to start fuzzing, the start does tend to become a little bit different, but the process eventually becomes the same regardless of how you start. It's basically just a question of how you're going to get that initial foothold to find a starting point. Now, number one thing I can say is before you start, Google a lot. A big part of fleshing out unknown file formats or poorly documented file formats is to try and see if anyone else has attempted this before and if they've posted any of their prior research, as well as if there's any hints from vendors, other researchers, etc. In this particular case, the outermost structures of link files are formally documented, and there has been a lot of prior reversing work on a lot of the nested structures, just not to the same level as what we did. So when you start with a vulnerability, you generally are doing this because you have a specific function as a starting point. So this is either something that was disclosed publicly by the vendor, the vulnerability discoverer, or another researcher. This also can be a potentially relevant function that you found from doing a binary diff. And I could talk for many days on binary diffing and all that kind of stuff, and unfortunately can't really get into that, but this is typically what we do when we're looking at a fixed vulnerabilities. We'll do a binary diff, and that's what we did in this case. So what you're first going to do is you're going to use the program to create a baseline normal file. So in this particular case, I just created a regular link file out of curiosity just to see what it would do. And your first step is basically try the long shot. You're going to set a breakpoint for your chosen functions in your debugger. You're going to load the file up in the application, and you're going to hope you get lucky and hit that particular function that you've chosen. If it does hit, you can then start the process of tracing data. However, a lot of times this doesn't work, especially with very mature software where a vulnerability may be found in a fairly obscure piece of code that isn't often reachable. So if this doesn't work, you do have to play around a bit with creating normal files. In this particular case, it did take me a couple of hours to figure out how to create a normal save search link file in this particular format. And in all honesty, it was a function of Windows that I didn't know existed until I started working on this. So it was very strange to me. Okay, so like any game you play, you kind of start out with the tutorial level. And in this particular case, it started out sort of easy. So when we looked at the bin diff, the only function that was changed in structured query.dll, which I knew from the prior research that was what we should probably look at, there was only that one function change, read prop variant, which, as I said, was the same function that we had dealt with before. So in terms of starting to flesh out that file structure, lucky for me, there was a call to a function called iStreamRead right away. So the first thing you do when you encounter an interesting looking function, get on Google and see if it's publicly documented, especially if we're talking Windows-based targets. That function is publicly documented, so we know what the arguments are. The second argument, which is in RDX, is the buffer that's going to contain the data to be read. And the third argument, which is R8, is going to be the number of bytes to read. So basically, if you look at that loadout from IDA there, you can see that 2 is being loaded into R8, and RDX is going to be our buffer that contains the data that we read. So from there, again, just like in a game, you started out, there's been a little bit of a tutorial, and now you kind of start to explore your surroundings. So in this particular case, we have to first confirm the data being read is actually coming from the file. We want to make sure that that iStreamRead call is actually pulling in information from the file, so we kind of know where we are. It's essentially like being able to pinpoint yourself on a map. So we check the 2 bytes that were read with iStreamRead, and in the particular file that I used, which was my normal file, it read hex 1F00. Not really ideal. It's not a particularly unique 2 bytes. But so there's 11 occurrences of that in our file. So we have to now expand the amount of data we're searching for to narrow down where we are and find, okay, this is what our starting location is right now. So essentially what we're going to do is we're going to check the value of the next read, and then we're going to add those bytes to the search, or we can also debug the entire read function to see the source data, which if you use WinDbg Preview is actually going to be pretty quick. So in general, I tend not to advocate for specific tools. You know, every tool has their positive and negative, but I can go on for days about how awesome WinDbg Preview is. It's going to save you tons of time doing tasks like this. And in all honesty, I truly believe that this is probably one of the most important tool releases in, I would wager, probably 5 or 6 years at least. So the big reason for this is that it has time travel debugging, which lets you go backwards and you can search through memory through the entire execution of a program. The recently added timeline feature makes tracing data an absolute dream. And this is really useful for when you can't trace data flow using static analysis. So almost any Windows component you deal with is going to be sort of C++ object-based stuff. And there's a lot of indirect calls that go on there, so you can't trace cross-references and stuff when you're doing static analysis of that. So in this particular case, we want to find out where those 2 bytes from the iStream read actually came from. And essentially what we do in WinDbg Preview is we add a memory write timeline item for the buffer. So you can see on the left there, I'm adding a new timeline. We pick a start address, end address, looking for just a 2-byte write at our destination buffer. And that basically shows me on that little timeline on the right there, these yellow diamonds, which is where writes are taking place. And when I mouse over them, you can see what value was actually written at that point in time to that memory address. So that way you can sort of really quickly be sure that the value you're looking for is being written at that exact location. And once you find that, you can literally just double click on that little diamond and WinDbg Preview will jump to that exact point in time you know, in the debug process. So that value was written in this particular location you see below here during a memcopy. So we can easily inspect the memory at the source, which is that the address stored in RDX, and we can very quickly see if we're in the file. So if you look on the left there, that's our RDX memory location, and you know, you can look at the memory before, you can look at the memory after. Even just adding the single byte after dropped us down to 3 matches in the file, and they were all clustered very close together. But due to some repetitive structures, I had to basically include 28 bytes before our 1S value, but that got me a unique spot in the file that you see highlighted on the right there. But you will notice that we're pretty far into the file. We're at an offset of, you know, like over 5B, and, you know, or 5B0, and that's pretty far into the file. So we are quite a ways in. So now we want to start establishing the structures in the file. We now know where we are in the file, and we do know at least one function that reads our file data. This isn't necessarily the only function that reads data from our file, though. Different file types may use a lot of different you know, methods of reading stuff depending on what's going on. But we do need to now figure out what got us here. So how did we actually get to this point way far into the file? So the first thing to do is to have a look at the call stack. If you have debug symbols, as the function names are almost always helpful. In this case, since we know we're dealing with a shell link, the highest C shell link call on the stack makes sense as a starting point. So you can see a bit of the call stack there. You will also notice that that is the hex 19th function in the call stack. So it is a really big, deep call stack. So there's a lot going on here. But what you can do in WinDbg Preview is you can do step it back or set a breakpoint on that particular function, and instead of going forward, you click go back until you get to your desired function. It's sometimes helpful to keep a breakpoint set on the identified read function. That way you can keep an eye on where in the file you are and if the function is still being called. It also can't hurt to keep notes of how many bytes are being read on each of those calls you hit, or at least make a mental note of where most of your reads are taking place. So, if you want to just breeze through and get to that parent function, at least be aware of, okay, all of a sudden this read function that I identified isn't being called anymore in any of these other functions. So that's where you need to sort of identify other ways that file data is being read. So now, as we're trying to find our way back to the beginning, and I get to the start of that C shell link function I talked about, I re-enable the iStream read breakpoint, and I see when I hit the next one. So finding the first read after the start of this function, we're going to see where we are in the file using the same method we did before. Unfortunately, the first iStream read encounter is quite far into the call stack. We're still pretty far into the file. Notice what I've highlighted there on the right. We're at just over 380 hex, which is, again, still pretty far in. So now what the goal here is, we want to keep tracing the original source of the data. So what we do is we set a timeline in WinDbg Preview for memory writes to the source for the read. So that address in RDX where our data came from previously had to get there somehow. We look for memory writes to that location, jump to that time, find the source, and then we see how that data got there. And we're basically just going to repeat this until you can't find any more writes or it seems obvious you're reading directly from the file. So it's very much an iterative process there. And so several timelines later, I believe this took me roughly 2 or 3 instances of, look for the source for this one, look for the source for this one, look for the source for this one. And then we eventually hit a function that's responsible for loading the ID list from the link file. So link files get loaded into memory by C shell link load from stream. We know that shell links have an ID list structure. This is from the Microsoft documentation. We don't necessarily know the detailed structure of all the different item ID types. So, loading the whole ID list, which is really a core part of the link file, is a really good place to start fully investigating the structure. And at this point, we can now start investigating the ID list from the start because we've actually identified where that ID list gets loaded. And, we're 16 slides in here, and we're what I would call just getting started. The goal is now to start enumerating generic structures. And what I say by generic structures is, you aren't necessarily going to know what these things are right away. You're just going to know, okay, it reads 2 bytes here, 4 bytes here, 5 bytes here, whatever. And so you just start building that out gradually. So what we're going to do is, we've hit that function that we've identified. Here's the real source of the data. We're going to step out of that function forward until we're back at the exit of the function that was called from IL load from stream EX. The ID list has basically just been loaded at this point, so anytime past that point, it may start getting processed, which is where we need to pay attention in order to figure out what's in that file exactly. So we're now looking at the file data right after the header, which is where those item ID structures start. So on the left there, that's what was copied into our new buffer in that IL load from stream EX function. You can see it starts with BD02. And on the right there, you can see in our hex editor, you can see BD02. And I'll also point out that the 2 bytes before that, you'll see those, that is the total length of the entire item ID list. So that's basically, absolutely all the chunk of data that follows that's considered part of the ID list is going to be contained within that many bytes. And just a side note, these are in little endian byte order, so really it's hex 75E and hex 2BD. So right now, at the very least, we do know item IDs start with a 2-byte length. So we also know that that hex 2BD is our length of our item ID, even though we don't know what's in that item ID. So now let's talk really quickly about the generalized process of how we actually approach this from this point. Now that we kind of have a foothold, we have a starting point in which to look at. You need to take extensive notes. When noting a new field, I highly suggest keeping track of the following: the field size and location in the file, the value in the file, the locations in the code where the value is read and used, and if you have a hypothesis for what the field might be based on context, throw it in your notes. My notes are full of completely wrong guesses at what's going on, but it really helps with your entire thought process and solving this puzzle. So the next thing to do is you want to check for the next read of the file data. You want to step out backwards of that read to see if the amount of data read is fixed or based on a variable. You know, files tend to be processed sequentially, so we do want to see what happens each time that file data is read. So basically, if it turns out to be a fixed amount, mark it down as a field. Say, okay, 2 bytes field. Don't know what it is. Then pay attention to what happens with it. So keep debugging and see if that value gets used very quickly, or if it's stored in a structure or something like that. If the amount of data read is variable, that's when you want to step backwards and you want to check where the value of the data amount came from. Did it come from a previous read? If so, hey, you just identified a previous field that was a length field. So you can now say, okay, these 2 bytes correspond to a length. You also really need to watch out for the data being copied elsewhere. So really, this is going to happen a lot where, especially when you're dealing with complex file formats, they may copy an entire chunk of a file into one place, and then they may copy a chunk in that file to another place. So you wind up with multiple copies of the same thing quite frequently. And regarding, the stepping out backward, just as an example, with our iStream read, we can see when a fixed length gets passed into the code. So an immediate value basically gets copied into R8, which I mentioned contains the amount of data that iStream read is going to read. Or when it's a variable, you'll see some other value get put in there. But quite frequently, you would see iStream read get called with an immediate value getting put into the R8 register. So what does this sort of generalized process look like in action? Well, we look for the next read of the file data. It's in ID list container is consistent. This turns out to be just a basic check to ensure item IDs have acceptable sizes given the ID list size. So the function basically iterates through, says, okay, let's check this length. Is there enough data left in this ID list to contain this? Yes, okay, let's jump to the next one, check its size. So shortly after that happens, the data is read twice in a function called ilCloneParent. The second of those 2 accesses is in a mem copy of 75E bytes, which is basically the size of our entire ID list structure. We can then use a timeline in WinDbg to determine when the destination for this mem copy is accessed. So basically, here's that copy that I mentioned where the file content is now being copied into a different buffer. So we need to now watch that new buffer. The destination does get accessed in another function, creg folder, create cached reg folder. So we step through this function to see what happens with the data. So this is part of establishing context and sort of trying to build a bit of an early understanding of what's actually going on. And this also lets us see if, we may not be doing really formal reads of every byte, but you can see sort of sequences starting to build. So in this particular case, this is a quick little screenshot from IDA. We see the item ID size at the start of the buffer being accessed in the very first block at the top there, where I've said check item ID size. It's basically just checking to make sure it's a minimum size. And then we're going to see a 2-byte value being copied into EDX from an offset of 4 from our buffer. And then that value plus 26 hex is compared against our item ID size. If it fits in our item ID, we use that value to read a value beyond that block of data, and that's in the 3rd block there where I've left that comment. Now, in this particular case, we can already basically establish that there's a 2-byte value at an offset of 4 is very likely a length, and it's followed by that many bytes of data, followed by the value that gets read into the XMM0 register. So this brings me to talking about how important it is to really start spotting patterns and picking out unique data. So as you're debugging, you'll begin to see certain patterns repeat themselves. In create cached reg folder, we see move UPS that uses XMM registers, which is, you're not necessarily going to see that a lot in something like this. But this pattern you do see anytime a GUID is being read. And a GUID is basically just, a 16-byte string that is a globally unique identifier. It's used all over the place in Windows. Now, it may not be apparent at first, but even a small amount of searching regarding link files will show you that GUIDs are very commonplace in link files. So when you encounter unique things, like really, unique strings of bytes or interesting instructions, it really can't hurt to Google them. Even Google, the actual bytes. It is also helpful to search for unique byte patterns in the applications and note their usage or if they have any associated name. So in this particular case, we found a cross-reference to a function called create cache delegate folder. So on the left there, we had 5 bytes of our GUID. We searched for that set of bytes in IDA, and then we came up with 2 cross-references or like 2 occurrences, and one of those occurrences only had 1 cross-reference, which is for this create cache delegate folder. And this was basically enough information to get me looking for more info on what delegate folders were. And this led me to some prior information from earlier reverse engineering efforts that have been publicly published. So far, we have a tiny little bit of work starting to build out this first item ID structure. We've now established the 2-byte item ID length, which was from the Microsoft documentation. We don't know what those next 2 bytes are. At the moment, we don't really care. We do know that the next 2 bytes are a length, followed by that many bytes of data, and then we do know that a GUID will follow right after. So obviously, there's no magic formula to reversing a file format. It's going to be different every time you approach it. Every file format is going to be different. Every situation is going to be different. And I wish we had time to go into great detail about how I enumerated each individual structure and field, but that would take forever, and it's not nearly as exciting as going and trying it for yourself. But let's look at a high-level overview of the resulting process I wound up going through, where I constantly applied some of the techniques that we just talked about. So first thing I did was I established that whole delegate folder item ID. That I found basically causes the next item ID in the item ID list to be handled by windows.storage.search.dll, and that's if the GUID that follows our first GUID that we just talked about corresponds to class ID search folder. There was some public work on this structure available to kind of get me started. So again, keep searching for info as you uncover more. I also determined that the property format GUID and ID, which creates a property key or P key for property stores contained in property store lists. So this is somewhat documented by Microsoft, but the actual format of very few P keys are documented. The P key basically determines the format of the property data itself. So it may say, okay, here's this particular property key, and the only way you know how to interpret the data contained in that property is if you know the format for that particular P key. So the next thing I did is I stepped through all the iStream read calls that read the VT stream data that was contained in this property store. And this is how I really started building out general structures, because the VT stream was where any prior research had completely stopped. They basically said, oh, this is stream data. There's some interesting strings in here, but we don't really know what's in here. So that's where I really started to buckle down and flesh everything out. So anytime a value that looked like a GUID was encountered, I hunted for more information. I Googled, I would check the Windows SDK, and occasionally I would go and maybe look at some source code that may have come out many years ago that is potentially helpful. But we won't elaborate on that. Now, based on the GUID names and some class names, I was able to determine that P key filter info property, the VT stream data contained in there, corresponded to the conditions tag in search MS XML files, and these are basically XML files that contain saved searches. And basically, I was able to kind of see that this I condition interface, C filter condition, compound condition, and leaf condition classes all got involved. And basically, when I searched for leaf condition as well as some of the GUIDs encountered, I wound up finding a GitHub repo with a sample search MS file. So that kind of got the wheels spinning and made me think, hey, maybe these structures are very closely tied to each other, and they were. So at that point, I was then able to relate iStream read calls to specific search MS tags. So each time a condition load function was called, this is basically when an embedded structure was being read. So essentially the equivalent of a nested XML tag was being read at that point. At that point, I was able to discover the condition history attributes, which contain the search history for a single saved search session. So basically what happens when you do a search, if you search for something and then you add conditions to it, or you change your search parameters a little bit, it actually retains all those different iterations of your search. And so when you create this save search shortcut, it serializes all that history data. So if someone was searching and then saved that search, you could see every single change they made in that particular search session. And then this finally led me to the precise location of the property variant, which is contained in leaf condition structures. And this allowed me to create the most minimal POC file to trigger the link vulnerability, which is ultimately the goal of what our research is. Sorry, just trying to get to the next slide here. Okay, so I'm going to close it with just some general WinDbg time travel debugging tips, because there are some kind of fun little tricks to it. It has some little quirks. One thing is when you're using the timeline view, watch out for multiple timeline objects that happen very close together. So even if you zoom in all the way, it may be really difficult to click the correct one. If they are too close to the point where you literally you may see just the edge of one of them. You can use time travel debug objects in commands to get a text list. And if you check the WinDbg preview documentation on the Microsoft site, you'll see a list of all these with examples and stuff like that. The other thing I highly suggest is you should attach to processes right before you load the file when you're working on reversing a file. Time travel debug sessions can get really large, so it's always best to keep the recording as small as possible. Also, when you're doing things like memory searches, you're going to find a lot less, a lot fewer false positives when you're hunting through memory. Lastly, having page heap enabled, which is, basically where memory allocations are placed at the end of the page, and there's essentially so that if you have an incorrect memory access, that it'll cause an instant crash in the program. So for researchers like us, when we're hunting for a vulnerability, we frequently have page heap enabled, so we know exactly when we've hit an incorrect memory access. And however, having this enabled in time travel debug does create really big trace files, and it does cause the application to run extremely slow. So, sometimes you do need to have page heap on when you're doing this. It does work. Just be prepared that it does take a long time, and have lots of disk space and patience, and RAM can't hurt either. Anyways, that's everything from me. Thank you very much, everyone, for listening. I hope you learned something, and please feel free to ask me questions on Twitter. I'll be on Slack. So yeah, please just let me know if you have any questions, and I'll be happy to try and answer them as best I can.